Welcome to the webinar, Net Zero, the Emergence of an Ammonia Economy in Europe. My name is Yuan-Shen Yu, and I'm a Managing Director on the Energy Group here at Lux Research, and I will be moderating today's session. Presenting today is my colleague Renil Dalia, Principal Analyst. Now, some housekeeping. Throughout the webinar, you can type any questions you have in the questions box on your screen. Time permitting, we will answer all the questions that we can. If your question does not get answered, please do not hesitate to email it to questions@luxresearchinc.com and we will respond. Now, let's jump into the presentation.
Great. Thank you very much, Yuan-Shen, and good morning, good afternoon, good evening to anyone listening. Very happy to be here today to discuss the hydrogen economy with a special focus on ammonia in Asia. So let's get started right away. When it comes to hydrogen, I don't think I need to explain why hydrogen will be needed in the future. I believe everyone listening today knows that hydrogen will be required for us to reach carbon neutrality by 2050. However, there's still a lot of questions that remains around the hydrogen economy. And one of the major questions is how much hydrogen will we need in the future in order for us to reach carbon neutrality? So today we are actually already producing 100 million tons of hydrogen, and most of that hydrogen is going to the refining and to the fertilizer sector for the production of fossil ammonia. So this is a current market for hydrogen. But if you look at 2050, and if you look at carbon neutrality, you can see that the amount of hydrogen that we will need will be much larger in the future. Now, there are many projections out there looking at how much hydrogen will be needed for us to reach carbon neutrality by 2050. What you see here is a projection by IRENA, the International Renewable Energy Agency, where they expect that we will need up to 600 million tons of hydrogen in the future. IEA's projection is a little bit less than that, so around 500 million tons, but altogether you can expect a growth of more than 3 to 4 times the current market for hydrogen today. Now, in 2050, we'll be using hydrogen for all types of application. We will still be using it in industry for refining and for ammonia production, but some new industrial applications will include steel making, for example. But we'll also be using low carbon hydrogen for the production of electricity, power production, as well as using that hydrogen as a fuel for transportation, whether that's road, marine, or even in some cases, aviation as well. So clearly, in the next 30 years, we will be needing a lot more hydrogen than we are using today. But where will this hydrogen come from, and where will this hydrogen go? And this is really a very hot debate today, because when you look at this figure from IRENA, you can see that not every country is equal when it comes to production and demand of hydrogen in the future. So IRENA did this analysis looking at where hydrogen will be coming from and where hydrogen will go in the future. And it's a very simple figure to understand. Essentially, if you're above the line, that means that you'll be a net producer of hydrogen, whereas if you're below the line, you'll be a net consumer of hydrogen. So the countries above the lines are the countries that have a lot of potential for renewable electricity in the future, simply because they have a lot of wind, they have a lot of sun, or both of them. And these countries include Australia, for example, Italy, Colombia, and so on. Whereas countries below the lines are countries that will not be able to produce enough hydrogen to meet their own demand. So these countries would include large industrial nations like Europe, for example, Japan, Korea, and so on. So when you look at these countries below, for Asia specifically, Japan and Korea are the big noteworthy countries. These two countries have a very large industrial base that is today run on fossil fuel, crude oil, and natural gas. If these countries want to decarbonize, and they do want to decarbonize, they do have a target for decarbonization, then they will need a lot more hydrogen that they can produce in the future. So where will this hydrogen come from? It can perhaps come from Australia, because as you can see in the figure, Australia will be a net producer of hydrogen. They will be producing more low-carbon hydrogen that they can use, which means that Australia could potentially send that hydrogen to Japan and to Korea. And this is not a hypothetical scenario. This is something that is already being discussed today. This is something that companies and project developers are already preparing for, essentially using Australia as a base to produce low carbon hydrogen and exporting that low carbon hydrogen to countries that do not have or will not have enough hydrogen in the future, in this case, both Japan and Korea. Now, if you are producing low carbon hydrogen in Australia, how do you get it over 5,000 nautical miles away to Japan and to Korea? There are different options that you can use for this. And today, these are the three main contenders for the long distance transport of hydrogen. These are liquefied hydrogen, where you cool hydrogen down to very low temperatures. You liquefy it, put it on a tanker, and send it abroad. You can use ammonia. Essentially, you combine the hydrogen with nitrogen to produce a molecule of ammonia, which you then send internationally. Or you can use a liquid organic carrier, in most cases, toluene or benzotoluene, to do the same. So today, no one is doing so at a commercial scale. No one is transporting hydrogen via either these carriers at a commercial scale. This is all currently at the early stage today. And each of these carriers have their own advantage and disadvantages. So quickly looking at the characteristics of these carriers, starting with liquefied hydrogen. So as I mentioned, with liquefied hydrogen, you essentially cool the hydrogen gas down to very low temperatures of less than minus 200 degrees Celsius. You liquefy it, you put it in a tanker, and you send it abroad. What are the advantages of liquefaction? The big advantage is the fact that the hydrogen remains in its pure state throughout the cycle. So you end up with very, very pure hydrogen. The disadvantage is the fact that one, it's a very energy intensive process to cool the hydrogen down to very low temperatures. And two, today there is no tanker that can carry hydrogen, large volumes of liquid hydrogen at the commercial scale. So on top of developing the liquefaction facilities, you also need to develop the vessels that will carry that liquid hydrogen to its destination. And this is happening today. The development is happening today. What you see here is a joint venture by different companies, with Kawasaki leading in this joint venture. So this is essentially a project that is meant, or that has demonstrated the transport of liquefied hydrogen from Australia to Kobe in Japan, and this happened last year. So this was a very small project. The goal of that project was just for demonstration purposes, where Kawasaki provided a vessel to showcase the feasibility of transporting liquid hydrogen over 5,000 nautical miles. And that project had some issues in the beginning, but eventually it was successful. And now the joint venture is looking at scaling to the commercial phase and really looking at starting to produce and transport large amounts of low carbon hydrogen, over 200,000 tons of hydrogen per year. So this is an example of a project in Asia around liquid hydrogen. But liquefaction is not the only way that you can transport hydrogen. You can also use ammonia to do this. So here you're combining hydrogen with nitrogen to produce a molecule of ammonia, and you then carry that to its destination. Now, the advantage of ammonia is, one, it has a very high hydrogen storage density, much more than liquid hydrogen or the organic carriers. And the second advantage is the fact that you have an existing infrastructure for ammonia. Ammonia today this is not a new thing. Ammonia is used as a fertilizer around the world, which means that it's already been traded around the world. Now, no one is using ammonia as a carrier for hydrogen, but people are using ammonia as a fertilizer, which means that if you want to start using ammonia as a carrier for hydrogen, you can actually leverage the existing infrastructure for ammonia. You can leverage the existing ammonia tankers. You can leverage the existing ammonia export and import facilities at ports today. So this is a big advantage of ammonia, the fact that you already have an existing infrastructure for it. The disadvantage is around the toxicity. Ammonia is highly toxic. And the other drawback is that today You can easily make ammonia, you can easily transport ammonia. However, you still cannot crack the ammonia to extract the hydrogen out of it at the commercial stage. So that last bit of the ammonia value chain, cracking, is currently still in development. So today, even though ammonia is already a globally traded commodity, there is activity looking at using ammonia as a carrier for low carbon hydrogen. And this project here between Korea Zinc, SK Gas, and Hanwha, among others, is looking at building a large-scale green hydrogen project in Australia in order to produce green ammonia in Australia and export it to South Korea. So this is currently still in the feasibility stage. Investment decision is expected in the next 5 to 6 years, but this is just one of many green ammonia projects being announced around the world, a lot of them in Asia, but also a lot of them in Europe as well. Now, the third options you have to transport hydrogen from Australia to Japan and Korea is by using an organic carrier. So here you're essentially trapping the hydrogen molecule into a chemical. In most cases, it's toluene or benzyltoluene. You put the hydrogenated chemical onto a tanker, you send it to Japan and Korea, you extract the hydrogen out of the chemical, and you bring the chemical back to Australia in order to fill it up again. Now, the advantage of the organic carrier is that it has a mild toxicity and flammability, so it's quite safe to handle, and two, is compatible with fossil infrastructure. So you can use a same oil tanker to carry your organic carrier. You don't need to build a new ship like you would with, like you have to with liquefied hydrogen. The big disadvantage is the fact that you need to recycle the carrier. With liquid hydrogen or with ammonia, you fill your ship up in Australia, you send it to Japan or Korea, you take out the ammonia and the liquid hydrogen, the ship goes back to Australia empty. With the organic carrier, this is not the case. Once you get to Korea and Japan and you extract the hydrogen out, you need to carry the carrier all the way back to Australia. And if you have to carry the carrier all the way back to Australia, that means the ship will be heavier, you're burning more fuel in order to bring it back. So the cost of transport will then become more expensive. So this is a disadvantage of the organic carrier, the fact that you have to carry a lot of the chemical back to its original source. So organic carriers today are currently at the early stage, and there are a few companies active in the space. One of the newer entrants in this space is ENEOS, the Japanese company. They have their own organic carrier technology, and they're looking at deploying this at scale, starting with a demo project that they just launched in Brisbane in Australia that showcased the use of the carrier as a way to store and transport hydrogen. So the goal of this project is to only validate the technology at the demo scale. They haven't yet announced any large-scale commercial deployment yet, but we expect that ENEOS will do so once that demonstration project concludes in the new year. So essentially, if you're someone who is based in Japan and Korea, and you know that Australia is going to become a large producer of low-carbon hydrogen in the future, you have three options in order to get that hydrogen from Australia to your operations. You can work with ENEOS and use their organic carrier solution. You can work with the Korean companies to get ammonia from Australia, or you can work with the joint venture around liquefied hydrogen. So all three projects are currently at the early stage, currently validating the technologies, but we expect that all three technologies will be ready in the near future. The question then becomes, who do you work with? Which technology do you choose to transport your hydrogen? Now, when it comes to deciding which option to look at, you need to look at the cost of hydrogen transportation. And this is really where you can see the differentiation between the three options. So liquefied hydrogen, ammonia, and LHC, what we did is we looked at the cost of hydrogen transportation from Australia to Japan and Korea over 5,000 nautical miles using these three options. You can see here that overall, ammonia has the lowest cost of transportation. It's the cheapest option, carrying hydrogen from Australia to Japan will cost you around $2 per kilogram of hydrogen. This is on top of the cost of hydrogen production in Australia. If you're using liquid hydrogen, you're looking at around $2.50. If you're using LOHC, it's closer to $3 per kilogram of hydrogen. So ammonia is the cheaper option for carrying hydrogen. And again, remember the advantage of ammonia, the fact that you already have an existing infrastructure. So the combination of being the cheapest option plus existing infrastructure makes ammonia the best option to use when it comes to transporting hydrogen around the world, including from Australia to Japan and to Korea. So again, ammonia will be the best option to do so. So we expect that most companies in Japan and in Korea will be using ammonia as their carrier of choice to transport hydrogen from Australia to their region. So if ammonia is used, if ammonia is the carrier of choice, then what does the ammonia economy look like? What does the ammonia value chain look like? Now, as I mentioned today, ammonia is not new. Ammonia is something that has been around for many, many decades now, but today all ammonia is coming from natural gas. So today you take natural gas, you reform the natural gas into syngas, you feed the syngas and the nitrogen into the Haber-Bosch reactor in order to produce ammonia. Now, this is what is being done today, but when it comes to low carbon ammonia, green ammonia, you will not be using natural gas. Instead, what you will be using is electrolysis. So for green ammonia, you're replacing your steam reformer with a water electrolyzer, and you also need a source of nitrogen, which comes from the air separation unit. You combine the two, and then you feed the hydrogen and the nitrogen into the Haber-Bosch reactor to produce green ammonia. So this is the green ammonia process, and the key here is really the Haber-Bosch system, because water electrolyzers are available and will be available in the future as well. Many more water electrolyzers will be available in the future. Now, when you look at ammonia production, the key technology is Haber-Bosch, and today this is commercial. But when it comes to green ammonia, there are many new companies active in the space. So what you see here is a selection of companies in ammonia generation. Now, what you see on top here, the first two columns are the large corporations. So these are the companies that are already today operating at scale, but with fossil ammonia, not green ammonia. And yet, all of these companies have plans to move to green ammonia. But it's not just large corporations active in the space. You also have a number of startups now looking at innovating in Haber-Bosch, innovating in ammonia generation. So companies like Starfire Energy in the US, or Copernic again in the US, or Fuel Positive in Canada, all of these companies are looking at deploying new type of catalysts, new type of reactors, specially designed for green ammonia production. So they're currently looking at small-scale operations only, producing ammonia on site for fertilizer usage, but eventually they will be scaling their platform up to the commercial stage. So in the future, you will have many companies, many choice of potential partners in order to scale your green ammonia production facility. But what's the challenge when it comes to green ammonia as a whole? You can see here that in the figure below, green ammonia requires a combination of water electrolysis and Haber-Bosch. Now, these two technologies are very different in nature. Electrolyzers are electrochemical in nature, whereas Haber-Bosch technology is thermochemical in nature. Now, it's not so easy to combine electrochemistry with thermochemistry in one process. Why is that? Because the advantage of electrochemistry is that it's quite flexible. You can vary the input, you can vary the input of electricity, you can vary the input of feedstock into the electrolyzer. Whereas with Haber-Bosch, you're operating at very high temperatures and pressures, and it's not so easy to be flexible with Haber-Bosch because you can't easily change the condition, the reaction conditions. And in the case of green ammonia, this is needed because your electrolyzer will be connected to, let's say, a wind turbine, for example, which means that the input of electricity in your electrolyzer will vary, and that means that your output of hydrogen from the electrolyzer will vary. But the Haber-Bosch reactor does not like having a variable input of hydrogen into the process. So how do you connect the two? In most cases, you end up building an over supply of hydrogen for your Haber-Bosch reactor. So you end up with a very large hydrogen storage unit in between the water electrolyzer and the Haber-Bosch reactor. But there are ways to simplify this, and this is what Topsoe and Vestas are both working on. So what these two companies are working on is essentially a dynamic green ammonia production unit where you connect the electrolyzer directly to a wind turbine. So this is dynamic hydrogen production. But Topsoe is also contributing a dynamic Haber-Bosch reactor that can handle fluctuations in hydrogen input. So before, there was no need for a flexible Haber-Bosch reactor because you simply did not have a flexible input of hydrogen in the process when you're using natural gas. But with green hydrogen, you will need such type of reactor. So this is currently still at the early stage. The first demonstration unit is expected to come online this year. And depending on the success of that demo unit, we expect Topsoe will, if it's successful, Topsoe will likely use that reactor system in the many green ammonia projects that they have planned around the world today. So this is one solution that Topsoe is developing, essentially minimizing adapting the Haber-Bosch reactor in order to handle the dynamic operations of a water electrolyzer. But is there something more that you can do with green ammonia? And the answer to that is yes. You can actually get rid of Haber-Bosch altogether and simply convert the entire process into a fully electrochemical platform. And this is known as nitrogen electrolysis, where you feed in air and water directly into one single electrolyzer system to produce ammonia directly from air and water. So in this platform here, you don't need to go to hydrogen. You can directly produce ammonia in the system. This is currently still very, very early stage. This is currently still at the lab scale. And one of the main companies, main startups active in this space is Jupiter Ionics. So Jupiter Ionics are currently developing this platform, this electrolyzer platform, where they are using a phosphonium salt as an electrolyte in the system in order to produce ammonia directly from air and water. Now, it's a very interesting platform. It's potentially highly disruptive, but really early stage, and we don't expect this platform to be commercial until after 2030. So in the near term, in at least the next 5 to 10 years, we expect that Haber-Bosch technology will still be used for ammonia production. So here, you are producing low-carbon ammonia, green ammonia in Australia. You have that in the facility, you put that in the ship, you then send the ammonia tanker all the way to Japan and Korea. Now, once you get to Japan and Korea, you need the hydrogen out of the ammonia. So this is known as a technology called as ammonia cracking, where here you feed in the ammonia into a thermochemical reactor. You heat the ammonia up to very high temperatures in the presence of a catalyst, where you then crack the ammonia and you essentially extract hydrogen out of the ammonia. And the nitrogen, you just simply release it in the air. Now today, ammonia cracking is not yet commercial. It's a technology that is currently at the pilot scale, currently still in development. The big challenge with ammonia cracking is its energy intensity. Now why is that? With ammonia cracking, in order to crack all of the ammonia into hydrogen and nitrogen, you need to go to very high temperatures. And you need to go to temperatures above 600 degrees Celsius. Why is that? It's because you want to have a very pure hydrogen coming out of your unit. You do not want to have trace ammonia in your hydrogen because ammonia is very reactive. If you have hydrogen with trace ammonia and you put that, say, in your gas turbine or into your fuel cell, you essentially destroy your fuel cell simply because of how reactive ammonia is. So in order to ensure that there's no trace ammonia in your system, you need to go to very high temperatures. And if you go to very high temperatures, you need a lot of energy. If you need a lot of energy, you need a lot of money, which is why ammonia cracking today is a very expensive technology, largely because of the amount of energy you need to run the process. But there are many companies working on solving this energy issue. And what you see here on this figure is all the companies working on ammonia cracking today, from large corporations to startups as well. Now, today, no one is at the commercial stage. Everyone is still at the early stage. Topsoe is currently running a pilot scale facility on ammonia cracking today, and they're looking at deploying a commercial scale platform very soon as well. But they're not the only one working on this technology. Johnson Matthey, Clariant, and BASF, and so on, are all working on catalyst for ammonia cracking, but you also have engineering companies like ThyssenKrupp, like KBR, also active in the space. But on top of these large corporations, you also have a number of startups that have popped up over the past couple of years that are trying to win that ammonia cracking race, and they are developing either novel catalysts for ammonia cracking or novel reactor systems for cracking the ammonia. So today, every company is at the early stage, but we expect the first commercial scale projects to be announced very soon. And this is already starting to happen around the world, including in Asia as well. Now, what you see here is a collaboration between CCG Plasmonic. They are a startup based in the US, and they have developed this photocatalytic cracking reactor in order to crack ammonia into hydrogen, back into hydrogen and nitrogen. And they are currently at the lab scale today, but they recently received investment and support from a number of Asian companies, Lotte Chemical and Sumitomo, among others, looking to deploy and scale this technology in South Korea. So initially, it will be a very small scale unit. It will be a pilot scale unit. And depending on the success of that project, they will then look at deploying larger scale systems in the future. And the first unit is expected to come online in Korea by 2024. So this is one company that is looking at essentially minimizing the cost of cracking. But the question is, do you actually need to crack ammonia in the first place? Because if, for example, you can use the ammonia directly, you skip cracking entirely. And this is really where ammonia shines, because if you don't need to crack ammonia, if you can use the ammonia directly, look at how much cheaper ammonia then becomes when you compare it with liquefaction and with the organic carriers. With liquefaction, it's very hard to make it cheaper because most of the cost of liquefaction comes in the liquefaction process itself. And with organic carriers, companies like Hydrogenous and so on are trying to find a way to use the organic carrier directly as a fuel, but it's very hard to do so. So it's unlikely that you will be able to use the organic carrier directly. You will always need to extract the hydrogen. On the other hand, with ammonia, there are efforts looking at using the ammonia directly, and one of the major ways to do so is in power generation. There are quite a few companies in Japan and Korea looking at burning ammonia directly for power generation. Because why would you take ammonia, crack it into hydrogen, and feed the hydrogen into a turbine when you can simply feed the ammonia directly into a turbine? Now, this is not yet commercial. This is currently still in development today. IHI is probably the leader in this space today. They have already tested a blend of 70% ammonia and 30% natural gas into a turbine. And they're now looking at raising that blend level to 100% by 2030. Now, burning ammonia in a turbine, this is not a simple project. It's not a simple process. It takes a lot of innovation, a lot of engineering know-how in order to adapt the turbine. And the main issue here is really the increased formation of NOx emissions in the process. But this is something that IHI, as well as Mitsubishi and other companies like Doosan and so on, are all working on. And we expect that the first commercial scale ammonia turbines will be online or will be available by 2030. And if this is successful, that is really cements ammonia's place as the primary carrier for hydrogen around the world. So what I showed earlier was essentially a very quick overview of how hydrogen and ammonia in particular will evolve in Asia. So the key takeaways from this presentation is, first, not every country in the world, including Japan and Korea in Asia, will be able to produce enough hydrogen. So they will have to rely on imports of hydrogen in order to meet the demand by 2050. And two, there are many carriers that these countries can use for transporting hydrogen, but ammonia will be the carrier of choice. Why? Because ammonia is or will be the cheapest carrier if you want pure hydrogen. It will definitely be the cheapest carrier if you can use ammonia directly, let's say in your gas turbine. And three, you already have an existing infrastructure for ammonia that you can leverage, which means that it becomes then the easiest to implement compared with hydrogen liquefaction, where you still need to develop the tankers, or with the organic carriers, where you still need to develop the value chain for these organic carriers. And third, the last takeaway here is really the role that ports will have to play in the ammonia economy. The role of ammonia is really as a carrier for hydrogen, which means that this ammonia will be exported at the ports and imported into the ports in Asia as well. So the ports really have a large influential role to play in the development of the ammonia economy. If a port decides that they will only be importing ammonia and not liquefied hydrogen or the organic carriers, then project developers will have no choice but to develop technologies and projects for ammonia. So if you're looking at entering this ammonia space, it's really worthwhile to take a look at the port that you will be working with, the port where the ammonia will come into, and collaborate with them, because the ports will be the first site for any hydrogen hubs, not only in Asia, but also around the world as well. So this is it from me today. I hope that this was helpful, and very happy to answer any questions you have on ammonia as well as the broader hydrogen economy as well.
Thanks, Renil. I think that second key takeaway is going to get a little bit of attention from our attendees today. But again, if you have any questions, please type them into the box on your screen. And we'll take a few now that you may have on the presentation. So again, if we do not get to your question on this call, someone from Lux will be in touch with you after the webinar. And for the first question we have here, unsurprisingly, if ammonia dominates the hydrogen carrier space, like you said, as the carrier choice, is there no role for liquefied hydrogen or liquid organic carriers in the hydrogen economy?
No, I wouldn't say so. Ammonia will definitely dominate the carrier space, but it doesn't mean that it will be the only carrier used by countries and companies around the world. And I think one of the major challenges with ammonia that is very hard to solve is the toxicity of ammonia. Ammonia is highly toxic. You breathe it in, you die. This is how toxic it is. So you can use ammonia, and like we are using today, right? We're transporting ammonia around the world, when it comes to large volumes and international shipments. But let's say you get into Japan and you want to use the hydrogen inland, you will not be able to take the ammonia from the port and transport it inland and then crack the ammonia next to your facility. You will not be able to do that because it's just too unsafe to do that. The population density is way too high. So what you will have to do is crack the ammonia at the port and then find a way to transport that hydrogen from the port to your industrial facility, either that the use of pipelines and so on. Whereas with liquefied hydrogen and the organic carriers, you don't have this problem. They are not toxic. They are flammable, yes, but there are ways to mitigate that. So you can potentially take an organic carrier all the way from Australia to a port in Korea, and then carry this carrier inland in Korea, extract the hydrogen out of the carrier next to a facility, and then carry the carrier back to the port in order to recycle it back to Australia. So that's the main disadvantage of ammonia. You will not be able to do it inland. And if you need the hydrogen inland and you don't want to rely on cracking at a port, then the organic carriers or liquefied hydrogen then becomes the better option. But we still think that in most cases, ammonia will still dominate in various applications.
Okay. I think since you talked about the transport of it on land, this next question that came through is kind of perfect. What about methanol? You didn't mention it. It's talked about
Yeah.
quite a bit for multiple applications, but will it not be used as a carrier?
Yeah, methanol is interesting. You often hear methanol in discussions around different carriers for hydrogen, and there's a reason why we didn't include methanol in the analysis, and the reason is carbon. It's simply carbon. With ammonia, or with the organic carriers, or even with liquefied hydrogen, with ammonia, for example, you only need to combine the hydrogen with nitrogen, which is widely available and very cheap to get as well. With the carrier, you need toluene and benzyl toluene, which are industrial commodities as well. With methanol, in order to produce methanol, you need to combine hydrogen with CO2. And where do you get the CO2 from? If you're using carbon capture from post-combustion, industrial facilities, then the CO2 is fossil in nature. So you can't really call your methanol as green methanol because the CO2 is fossil in nature. If you truly want to be green, then you need to get the CO2 either from biomass, which is limited in supply, or from direct air capture, which is very expensive. So you combine the hydrogen with a very expensive carbon atom, you transport it all the way to Japan, and then once you get to Japan, you crack the methanol to extract the hydrogen, and you release the CO2 back in the atmosphere. Now, why do that, right? It's a very expensive way to just transport the CO2 and then release it to the atmosphere. So in our opinion, methanol should not be used to transport hydrogen. Methanol should actually be used to transport carbon around the world. Now, if you don't have a source of renewable carbon or carbon neutral carbon in Japan, but you have it elsewhere, you can use the methanol to do that. And then once the methanol comes into your borders, you use the methanol houses to produce things like formaldehyde, acetic acid, and so on. So methanol should only be used if you're looking to use both carbon and hydrogen. But if you only want to use the hydrogen, then ammonia or liquefaction then presents are a better solution in this case.
Excellent. Well, thank you, Renil, and to all the attendees, that concludes our webinar for today. Again, the slide presentation and the recording from this webinar will be sent to all of you via email. So after leaving this webinar, you will be prompted to complete a survey on today's presentation. We'd really appreciate any feedback that may you have to help inform and improve our future webinars. Also, in regards to those future webinars, please take a moment and check those out. Thanks for joining us and have a great day.
Thank you.